Okay, I think I'm online now, yeah. Let me just see here. I just wanted to add this video to my website, so give me 2 seconds. I'm just running a little behind here, just 2 minutes behind schedule. Give me 2 more minutes. Okay, I gotta share, copy, go to the website, embed, YouTube video, paste, insert, move it to the top, and center, change the background color to gray, nope, dark blue. And we are live. Okay, great. All right, so last class, I guess that would have been on Friday of last week. We were looking at different number systems, and I posted a little bit of homework on number systems. So we're gonna sort of carry on in that vein today. We have to kind of go back and do just a little bit of review of a few topics before we move forward. I'd like us just to make sure that we're not skipping anything. Really, I mean, one of the main reasons why we look at number systems, well, there's many reasons why we look at number systems, but one of the big topics in number systems is, like, if I take the square root of a number, like the square root of, let's say, 80, or if I were to take the square root of 81, one of these is a rational number, and the other one isn't. Okay, this one, the square root of 81, that's equal to 9, and well, the square root of 80. Let me just pull out my calculator. I can't do that one in my head. The square root. Where's my square root symbol? There it is. Square root of 80. That's equal to like 8.944279191. That's an irrational. So this is an irrational number. This is an irrational number, and this is rational. In fact, this is natural as well. Okay, so this is kind of the context that we're going to be looking at number systems, is mostly with square roots. Square roots are where things get a little bit funky with different number systems. Square roots will give you irrational numbers. Square roots can also give you complex numbers. We talked a little bit about complex numbers. Like if you took the square root of -1, that's not a real number. This is not an element of the real numbers, right? Anyways, this is all messy, and I'm kind of just sort of blabbering. So let's get started. By the way, I apologize for the sound. Hold on, let me just stop talking and see what my mic looks like. Okay, it doesn't actually look too bad. There's people, like my neighbors are cleaning their yard, and they've got those blowers, and they're really loud. I think they're around the corner right now though, so hopefully it's not too much of a distraction. Also, I'm looking really dark in the camera right now. Change the light. Not that you really need that, but that might be a little bit better. How's this? Yeah, there's a little more light. Whatever. There was another. Oh yeah. I don't know if you guys have been seeing this on the internet. It's kind of gone a little bit viral. Rtx Voice. Have you heard of? I wonder if you've heard of that. Rtx Voice is it's made by NVIDIA, like those guys who make graphics cards for computers. And the cool thing about it is that it uses AI to remove background noise. So maybe I should install that, and then I wouldn't have to worry about my neighbors using their blowers. Okay, so I want to first talk a little bit about, so let me just tell you what we're going to talk about today. We're going to talk about factoring. So we've looked at factoring like trinomials. We did a lot of factoring of trinomials. What we're going to do today is we're actually going to just factor whole numbers. So I'm noticing that my computer screen is a great source of light, You can probably see my face light up. So what I'm going to do is I'm going to just have a nice bright white screen, or maybe I'll take YouTube out of dark mode. How do I do that? You know what? I'm getting distracted. I'm getting really distracted. Let's just jump right into it. Okay, so I think I can't see myself anymore, but I think this is probably just fine. Oh, maybe I'll do this. Yeah, I'll do this, and sorry, I just want to make sure that I'm set up and comfortable. And oh, is this not on? Oh, I didn't hit publish. Shoot. Why is it not publishing? Ah, here it is. Okay, it is published. Okay, so I'm just going to, there we go. Okay, now I feel a little bit better about this. Okay, I think that it's nice and bright, or bright enough. Anyway, okay, so we're going to talk about, okay, we'll talk about a few things. So topics for the day. So topics for today are the following. We are, and I mean, I'm going to make sort of like an exhaustive list. If we don't get to all the topics by the end of the class, so be it. But this is our goal. So our goal for today is to talk about the following things. I want to talk about prime power decomposition. Okay, prime power decomposition. I want to talk about LCMs and GCFs, and how to take a prime power decomposition and get LCMs and GCFs. So that's kind of the main thing that we're going to talk about today. And if we do have time, what I'd like to do is I'd like to talk about radicals. Okay, so those are the three big things that I want to talk about. I'm almost certain that we'll be able to get through this topic and this topic, but radicals, I'm not sure. I'm not sure if we'll have time to talk about it. And I understand that you guys do have some experience in the first two topics. So I know that you guys have done some prime power decomposition, and you certainly have taken some LCMs and GCFs in your life before. But I'd like to show you some methods. These are methods that I haven't ever seen in a high school setting. But these are the methods that I used in university. And I think that they're really powerful methods, and I don't think that they're very hard to understand. A couple of weeks ago, it was actually my very last day working at Grant Park, like inside the physical school, the very last day. I think it was a Friday. I happened to bump into one of my old students at the University of Winnipeg. And she actually mentioned this method. She was like, I remember when you taught me this method of finding LCMs and GCFs, and I still remember how to do it, and I still do it to this day. So it was really sweet. It really like made me very happy that, I mean, that's the one thing that a math teacher can hope for, right? Is that a student remembers a cool method on how you taught something. So, I'm going to show you that method. It's a great method. I love this method very much. Yeah, let's just jump right into it. So first of all, what is a prime power decomposition? Well, let's talk about prime power decomposition. What does this mean? Okay, so let's talk about what this means. So given any number, so given any natural number, I should say, natural number, and I should say given any, okay, so given any natural number greater than 1, so it doesn't really work for the number 1, we kind of ignore the number 1. The number 1 is like, the number 1 and the number 0, those are two numbers that have a lot of exceptions. We say a lot of things about pretty much all the numbers, and then usually 1 and 0 kind of have their own special case. Anyway, so if I gave you any natural number greater than 1, we can write that number. We can write that number. You can probably hear my neighbors now. We can write that number as the product of prime powers. For example, let's try the number, I don't know, 24? 24? Okay, well 24, what's that equal to? Well, okay, well there's definitely a 2 in it. I think there's a 3 in it. There's a 4, there's no 5, there's a 6 in it, there's no 7, there's 8 is in it. 12 is in 24. 12 is a factor of 24. 24 is a factor of 24. 1 is a factor of 24. But what do I mean by prime powers? A product of prime powers. Well, a power, so a power, I'll just kind of on the side here. Okay, so a power looks like this. I've got a number to the power, or with an exponent of another number. Oh, you can't see that because my head is in the way. So I've got one number taken to the power of another number. Okay, so these are the prime powers. So basically, what I mean by a prime power, so a prime power, and there you go, a prime power is where this guy is prime. Okay, and I want to write 24 as a product of prime powers. So really what I'm going to do is I'm going to say, okay, well, what's the biggest power of 2 that is a factor of 24? Well, 2 is a factor of 24. 4 is a factor of 24, that's 2 to the 2, and 8 is a factor, 2 to the 3. 8 is a factor of 24, right? So this is 2 to the power of 3. That's what 8 is, right? This is equal to 8. And the other one is, so 8, what am I trying to do? Oh yeah, so 8 times 3 is 24. 3 is a prime number, so this is equal to 3. So this will be the prime power decomposition, okay? So this right here, I'm just going to erase this. You guys know that's equal to 8. So this is the prime power decomposition of 24, okay? It's a prime power decomposition because I've written it as powers. If I wanted to, what you may have seen this before too, you may have seen, so I'll just write note, 24 is also equal to 2 times 2 times 2 times 3. This is not the prime power decomposition. This is the prime decomposition. Okay? Not the prime power decomposition, just the prime decomposition. So what we're going to be focusing on today is how to get the prime power decomposition. Okay? And I have a feeling you already know how to do this. I have a feeling that you did this with Mr. McIntosh probably in September. I think that he does a thing called the prime climb, and this is very much related to that. Okay, but sometimes it's good to do something more than once, right? Okay. So how to find the prime power decomposition of a number. Well, it's quite straightforward actually. Factor trees. This is, I say this a lot. I always say that something is my favorite, but factor trees really is one of my all-time favorite things to do in a math class. So factor trees. So let's try a nice big number. Let's do 60. Okay. So let's find I'm gonna write the prime power, the PPD, the prime power decomposition for 60. Okay. So let's go ahead and do that. So the prime power decomposition for 60 is, well, what I'm going to do is I'm going to write 60 over here in green. So here's 60, and the cool thing about factor trees is that it doesn't matter what order you choose your factors, and this is actually a major theorem in mathematics called the fundamental theorem of arithmetic, and that says that the prime power decomposition for a number is unique. Now I'll talk about that in a minute. So the idea here is that we can factor 60 in two ways. So this would be 6 times 10, right? Because 6 times 10 is 60, and 6 is 2 times 3, and 2 is a prime number, and 3 is a prime number, and 10 is written as 2 times 5. Both of these are prime numbers as well, so I circle them. It's really important in your factor trees to circle the prime numbers so you know that that branch of the tree is now a leaf. And even though it's kind of like the factor tree is upside down, right? It would almost be better. How do I do this? It would almost be better if now this looks more like a tree than the other one. The other one kind of looks more like roots of a tree, like the root system. Anyway, we call it a factor tree because it kind of looks like an upside down tree. Actually, it comes from graph theory. In graph theory, there's things called trees, and this is an example of a tree where all those numbers are little nodes of the tree, and a node is where the branches kind of branch off. Anyway, I'm getting really distracted today. I'm not sure why. Okay. So we found so these are all the factors. So these are all the prime factors of 60. Those are all the prime factors of 60. Okay? So the prime power decomposition would be, well, it's important to first off to write the number that you're talking about. So 60 is equal to, well, what I'm going to do is I'm going to write all these numbers again, except from least to greatest. So I'm gonna, whoops, gosh. Oh, looks like everything's okay. I just noticed there's a fuzzy screen on YouTube, but it looks like it fixed itself. Anyway, I'm gonna write all these prime numbers from least to greatest, okay? And I'm gonna write all the repetitions too. It's important that you, like 2 occurs like twice, right? Here's 2 once, and then here's 2 twice. Really important that 2 appears 2 times. So 60 is equal to 2 times 2 times 3 times 5. And you'll notice that I'm writing dots for multiplication. I prefer to use dots here. You could also do the cross if you wanted to. Doesn't really matter here. Anyway, we've got 2 times 2 times 3 times 5. So that's the prime decomposition. This is the prime decomposition. I'll write decomp. And the prime power decomposition is where I just say, okay, are there any repeated values? Well, yes, absolutely. So this would be 2 to the power of 2. So I've got 2 to the power of 2 times 3 times 5. And if you want, you could put a 1 here. Doesn't really matter, but you can kind of see that that there's some nice sort of symmetry there. Okay. Okay. All right. Good. So that's the prime power decomposition for 60. Okay. So I take it that you guys have sort of done this a little bit. If you wouldn't mind just saying so in the YouTube chat, if you have some experience with this, just kind of like a yes or no sort of thing. I don't need to know all the details of every little thing that you did, but if you wouldn't mind just saying in the chat, oh yeah, we've done this a little bit sort of thing. We've done this quite a bit. Okay, so you've got some experience. That's really good because I mean, you might be a little annoyed that you have to do it more, but like this is a really important topic, and having a good foundation in this really translates to a deeper understanding of other areas in mathematics, because this is kind of like the what I said here, and this is actually a really big point. this is the fact that this works, the fact that using factor trees works, this is a result of number theory that's called the fundamental theorem, the fundamental theorem of arithmetic. Okay? How important does that sound? I don't know about you, but that sounds pretty important to me, right? The fundamental theorem of arithmetic. That's just what we just did that. We just did the fundamental theorem of arithmetic. The fundamental theorem of arithmetic says, if you use a factor tree to factor a number, it doesn't matter where you factor your number. So let's try 60 in a different way. So we did 60 is equal to 6 times 10. What if we did 60 is equal to 2 times 30, right? Well, 2's prime. Well, 30 I can factor as 2 times 15, and 15 is equal to 3 times 5, right? We got the same thing, right? So the fundamental theorem of arithmetic says that it doesn't matter how you break down a number when you're factoring it. All that matters is the prime power decomposition, okay? This is an incredibly important topic in mathematics. I think that this is possibly one of the most important things to understand in mathematics. And I'm not the only one who thinks that, because this is called the fundamental theorem of arithmetic. If you could think of something more fundamental in arithmetic, then we would call that the fundamental theorem of arithmetic. But this seems to be the most important thing in all of arithmetic. Arithmetic, by the way, if you didn't know what arithmetic means, arithmetic just means adding, subtracting, multiplying, and dividing, and all the ins and outs of that. Okay, so since you have a little bit of experience with this, I'm not gonna sort of belabor the point. We're gonna talk about LCMs and GCFs. Okay, LCMs and GCFs. Okay, so so basically what the goal here is I'm going to give you the definition of least common multiple and greatest common factor, and we'll do just a couple of quick examples, and then I want to show you how to use the prime power decomposition to find the LCM and the GCF. Okay, that's our goal. So LCM, and like I said, I wouldn't be surprised if you have some experience with this already, but we're still gonna do a quick review. Okay, so LCM. So given two or more numbers, and I should say natural numbers, and they have to be greater than 1. So given two or more natural numbers greater than 1, actually, you know what? They could be equal to 1. They could be equal to 1, come to think of it. And in fact, you could talk about 0 being in this set, but just for the sake of being concise, for brevity, we're going to assume that our numbers are greater than or equal to 1. Otherwise, we'd have to talk about special cases. But it does work for 0. You can define a least common multiple that includes 0, but it's kind of a silly definition. Anyway, so if I gave you two or more natural numbers that are greater than or equal to 1, well, the LCM, or I should say the least common multiple, well, I mean, the least common, it's a very well-named definition, right? I mean, it is what it is. It's the least common multiple. It's a multiple of all the numbers. That is, it's a common multiple, so it's a multiple of all of them, and it's the smallest one that makes it so. But just for the sake of a good definition, the least common multiple of the numbers is the smallest multiple of all numbers. Okay, Okay, so and it's kind of it's sort of a circular definition. So let's just do a couple examples. I have a feeling that you've seen this before, right? I mean, in order to add fractions, you need to know what an LCM is. So, and I've seen you guys add fractions. So, yeah, you can do this. But just for the sake of you know moving things along, let's try some examples. So let's do an example. So let's find the LCM of, let's try, how about 6 and 8? 6 and 8, okay? Okay, and some notation that I like to use is, I could just write this all in one line by saying LCM and put in brackets 6 and 8, okay? So the LCM of 6 and 8, well, basically, I mean, like the most straightforward way to do this, and this is the way that we're going to unlearn, if this is the way that you already know how to do it, we're going to sort of undo that, and we're going to learn a new way. But one way to calculate the LCM is to say, okay, well, I got to look for all the multiples of 6, so I've got 6, 12, 18, 24, 30, etc. And then for the multiples of 8, so those are the multiples of 6. The multiples of 8 are, well, okay, I've got 8, I've got 16, I've got 24. Oh, look at that. I've got a common multiple. It's the first one on each list. And there you have it. So the LCM of 6 and 8 is 24. Fantastic. Okay, so we're done. I'm gonna, the whole goal of today's class, and I really hope that we can get to it and that we don't have to leave it for Thursday, but the whole goal is to learn a new method. Who is trading tuition? I'm not sure what that means. Okay, so that's our goal for today, is to learn sort of a more technical way of doing this. Because like, what if I were to ask you to find the LCM of like 2,468 and 9,084, right? Like, what if I asked you the LCM of that? You'd have a hard time, wouldn't you? Right? We'd be able to get the first multiple of this one, but you pretty much would have to resort to a calculator. I would like to show you methods of being able to calculate the LCM of these really big numbers without even using a calculator. That's what today's goal is. And it all works with the prime power decomposition. Okay, the GCF, let's talk about GCF. Okay, so GCF, so the greatest common factor of two or more natural numbers, and I should say greater than or equal to 1, is a factor of each number, I should say simultaneously, right? It's simultaneously a factor of all of the numbers in our set, which is as large as possible. Okay. So let's do a quick example. So let's do, oh, I know, how about the LCM of, so the GCF of 6 and 8. So calculate the GCF of 6 and 8. Okay, so the GCF of 6 and 8, well, again, we could make an exhaustive list, and this may be the method that you already know. So 6 has the following factors. It's got 1, 2, 3, not 4, not 5, 6. Okay. 8 has 1, 2, not 3, 4, not 5, not 6, but 8. And the largest number in this set, well, they both have 1 in them, but they also have 2 in them. So the GCF of 6 and 8 is 2. Okay? And again, you can kind of imagine the difficulty in finding the GCF of large numbers, right? So that's kind of our goal today, is to look at some of the cool methods using the prime power decomposition and factor trees and using that information to calculate the LCM and the GCF. This is really cool stuff. I really like doing this. I find it really fun because you can take these big numbers, right, and you can learn a lot about them by breaking them down. Okay, I think that mathematicians often think of the prime power decomposition almost like a fingerprint, like a thumbprint of a number, right? It's like your phone is only going to let you unlock it if it knows a little bit about your thumbprint, right? It's like everything, like your whole identity is sort of like stuck in. It's like your, you know, it says your thumbprint says a lot about you, right? And same with the prime power decomposition, is that it's kind of like your fingerprint of a number. Okay. All right. So I guess we can just jump right on into that. So let's go ahead with this. And again, if you have done this method, and I'm kind of talking it up as if like I invented it, like I didn't invent this method, but if you have done this method before, let me know, okay? Because I do want to know. Like I have like a pretty good idea of everything that you did last semester, but I don't have all of the facts. So if you've done this before, please let me know. But if you haven't, let me know as well. I just kind of want to know how much detail I should be telling you about all this stuff. Okay. So using the prime power decomposition to calculate LCMs and GCFs. Okay, so the way I'm going to do this, I'm going to just do a couple of examples, and I'm going to explain my thinking through the examples, and I'll make some notes as we go. Some things in math it's really hard to explain the theory without seeing an example alongside. You know, in university and in that kind of setting, a lot of classes is all just theory, and you just learn theory, and then a couple examples at the end. But I think for us it's better if we just do some examples and we can kind of see everything in action, and we sort of learn how it works as we go. Okay, so let's try some examples. So let's do this one. Let's start off just talking about LCMs, and then we'll do GCFs in a minute. So let's start with LCMs. Okay, so I'm gonna find the LCM of, let's do yeah, let's see. Yeah, this is a good one. Let's do 60 and 72. Okay, so calculate LCM of 60 and 72. Okay, so calculate the LCM of 60 and 72. Okay, that's my goal. Okay, so the way I'm going to do this is with a factor tree. So what I'm going to do is I'm going to factor 60 and I'm going to factor 72. So here's 60 and here's 72. Okay, so I'm going to factor these, and okay, anyway, okay, so factor trees. So I'm going to factor these, and okay, so this one is 6 times 10. I think we already did 60 here, which is fine. So just factor these right up. That's 2 and 5. Okay, so those are my prime factors, and I'll do the same thing with 72. 72 is what? That's 6 times 12, right? 6 times 12. 6 is 2 times 3. Okay, those are prime. And 12 is 3 times 4. And 4 is 2 times 2. Okay. So 60 is equal to, well, I've got 2 2s, so it's 2 to the power of 2 times 3 times 5. Okay, great. 72, on the other hand, 72 is, well, let's see, I've got 1, 2, 3 2s, so it's 2 to the power of 3, and I have 1, 2 3s, so 3 to the power of 2. Okay, awesome. So now here's what I have to do. So I'm going to use this information. To calculate the least common multiple. So a note about the least common multiple. So I'm just going to do a quick fact on the side here. So I'm going to give you this fact. Okay. If, let's say, if A is a factor of B and B is a factor, I'm going to use X, Y, and Z here actually, because I don't want you to confuse the word with the word or the letter B. So if X is a factor of Y and Y is a factor of Z, then X is a factor of Z. Okay, it's a fact. So it's kind of like X. If X goes into Y and Y goes into Z, then X goes into Z as well. You kind of get this sort of what mathematicians call a lattice. So for example, 2 goes into 6 and 6 goes into 12. Well, 2 goes into 12 as well, right? And I think that's fairly plain to see. So in that vein, we can use that fact to use this information to calculate the LCM of these two numbers, okay? So our least common multiple, so I'll just write LCM. So our LCM must have, okay, it must have 2 squared as a factor, right? Because 60 is going to be a factor of our LCM, right? Because our LCM is a multiple of 60, right? The LCM, whatever that number is that we find, it will be a multiple of 60, okay? Or in other words, 60 will be a factor of it. So all of the factors of 60 must be factors of our LCM. So it must have 2 to the power of 2 as a factor. It must have 3 as a factor. It must have 5 as a factor. Okay. It also has to have 2 cubed as a factor. Okay. It has to have 3 squared as a factor. Okay. It also must be as small as possible, right? Because it's the least common multiple, right? That's what the L is. It's the least common multiple, all right? Least, right? It's the least common multiple. So we can't just like take all these numbers and multiply them together, right? If you did multiply all of them together, then that would be the product. You'd just be multiplying these two numbers together, okay? But what we're going to do is we're going to look at the exponents, okay? So what I'm going to do is I'm going to go through here and say, okay, well, I've got a 2 here and I've got a 2 here. One of these has to be, well, they both actually have to be a factor of the LCM, but if 2 cubed is a factor, then that automatically means that 2 squared is a factor, okay? So if 2 cubed is a factor, then 2 squared must also be a factor. So we're going to ignore this one, okay? Now same with 3. So these two, we have to choose which one it's going to be. Well, if 3 squared is a factor, then 3 must be a factor as well. So I'm going to circle that one. I'm going to cross that one out. And then we've only got this 5, so we're good. So the LCM is going to be let's start with the 2. I've got 2 cubed times 3 squared times 5. And now we can multiply that out. That's equal to 8 times 9 times 5. 8 times 9 is what? 72. So I've got 72 times 5, which is, what's that? 360? I think that's 360. Right, because 4 times 9 is 36. Yeah. Okay. Yeah, so that's 360. So 360 is a multiple of 60, yeah, and 360 is a multiple of 72, absolutely. So we're done. That's how it works. So yeah, I guess what I'm going to do for the exit slip today is I'm going to just ask you about the methods that you've done to solve this. Keep in mind, we're not quite finished, and class is going to end in about 1 minute, so I have to wrap it up. The method that I'd like to show you is based on these facts, but really what I'm going for is what we're going to be doing tomorrow. I was hoping that we could do this today. Is we're going to make like a table, and our table is going to look something like this, okay? Where we would have like 60 and 72, and then what we would do is we would write all the prime powers in here, and so we would have something like 2 squared, 3 and 5, and then we would have 2 cubed and 3 squared, and then what I'd like to do is I'd like to circle these like this, and then that gives us both the least common multiple, and it also gives us the GCF at the same time. So how can you contact me if you have any further questions? You can send me an email, you can send me an Instagram message, you can go onto my Discord server and message me there. Those are the 3 ways that I communicate with students. So yeah. Okay, so I'm gonna wrap it up there. The exit slip for today is the following. So the exit slip, and I'm afraid there's not going to be any homework today because I wasn't able to finish showing you my methods. So we're gonna hold off. So no homework for the next 2 days because we don't have class tomorrow. But I'll certainly give you some on Friday, or sorry, Thursday. So the exit slip is to describe. I'd like you to describe how you know how to calculate LCMs and GCFs. Okay, that would really help me out just to know the methods that you're familiar with, so I can build off of that. Okay. Google Classroom. I prefer not having contact using Google Classroom. I find it challenging to use that for communication. Sometimes what happens is I'll get a notification on my phone that someone made a private comment somewhere, and I go log on, and then it kind of, the comment, it doesn't tell me where to find the comment. I just get a notification that I got a comment, and then I have to so please don't contact me through Google Classroom. If you have any concerns, to be honest, my favorite way of communicating is Discord. It seems to be the most seamless and easy to use communication system. So if you'd like to contact me, please contact me through Discord. My second favorite is email. That's my second favorite method of communication. And my third is Instagram. And my least favorite is Google Classroom. I really don't like communicating on that platform because I find it a little confusing. Or not so much confusing, but messages seem to just get lost and I can't seem to find them. So I know that one of my things on my never-ending list of things to do is to go over a Google Classroom, because I know that a couple students have sent me some messages. I don't know what the messages are. The notification is gone on my phone. So yeah, I've got to sort through that. So anyway, I'm going to sign out now, and I'll talk to you guys on Thursday. I hope you have a good day. And Goose would just like to quickly say goodbye. She misses you. And she'll see you on Thursday. Okay, bye-bye. Oh, and now she's going to lie on top of my iPad. Okay, bye-bye.